Hello, this is chapter 12, or lesson 3, about tolerancing. Our objectives for lesson 3 are, first of all, describe the nominal size, tolerance, limits, and allowance of two mating parts. Typically a shaft and a hole would be the mating parts. Identify a clearance fit, an interference fit, and a transition fit. Describe the basic hole and basic shaft systems. Number 4, calculate size limit dimensions of shaft and hole when given basis, nominal size, and standard class of fit. 5, dimension mating parts using limit dimensions, unilateral tolerances, and bilateral tolerances. And 6, describe the classes of fits and give examples of each. 7, differentiate between the various geometric symbols. We're going to talk a little bit about GD and T in this section as well. And then 8, draw basic feature control frames. And number 9, relate datum surfaces to degrees of freedom. So let's get started with tolerancing. A tolerance, that's the total amount a specific dimension is permitted to vary. In a lot of manufacturing operations, a lot of parts are machined, and those machined parts go together to form assemblies. And the tolerances determine how these parts fit together when you're making the assemblies. And really what the tolerances are is how much that part's permitted to vary after machining. There's tolerances of hole sizes, there's tolerances of feature locations, there's tolerances of part sizes, there's tolerance on angles, there's tolerances on any feature that you would have for a part. Okay, to effectively provide tolerances in your drawings and CAD models, you must understand the fit between mating parts and have a clear picture of how inspected measurements are performed, and be able to apply tolerance symbols to a drawing and apply functional tolerancing to individual parts. Now, it's very important that tolerances be calculated based on the function of the parts, which is kind of outside the scope of this course, but applying tolerances to drawings is very much a part of this, and how to properly assign tolerances and display those tolerances on the drawing is very much the topic of this course. Okay, quality control. Typically aerospace or many industries, parts need to be conform to their drawings. So all features on that part has to be within their specified tolerances, and typically parts will go through quality assurance plan to assure that the parts do indeed meet the drawings. Again, the tolerances that are specified on the part drawing are based on the product's fit and function. Okay, so now definitions for size designation. Right here we're talking about a fit. Okay, a feature here is feature in this case is a hole. A feature here is the diameter of this barrel, and that is a feature of size. It has a size associated to it. The nominal size is the nominal size. It typically does not apply a tolerance, where the actual size is the dimension that the part actually measures. Now, parts aren't perfect. Okay, so a perfect form envelope. Okay, you can think of tolerancing as defining the perfect form envelope that the real produced part must fit inside. So if the part is wasted, or it has bows in it, or it's tapered, or it's barreled, it still has to be tolerant such that it's going to fit at the next level assembly. And then this describes the material envelope. Okay, so in this particular case, we have a part. The part in green is a part. The thing you see wrapped around it is the actual mating envelope. It's just a graphical depiction of the item that this part fits into. And it's just for illustration purposes. Now, let's say, for instance, that this part had a bow and warpage. Okay, it is going to be outside that actual mating envelope, in which case that part's not going to fit at the next level assembly. So these are the things we need to be aware of when we're assigning tolerances. Okay, so here's about the fit between mating parts. This is a shaft and a hole. So a fit is the range of tightness or looseness resulting from the allowances and tolerances of mating parts. So what we're saying here is we have these two parts, and these two parts are made with their tolerances. Okay, so how are these parts going to fit together when you put them together? So in this particular case, I've got a shaft that's at 1.247, and then we've got this hole at 1.251. If I take the difference between those two, that would be 4 thousandths. Here we've got, that's the loosest fit. Now the tightest fit over here, based on our tolerance range, is we have a hole of 1.25 and a shaft of 1.248. If we take the hole and subtract the shaft, we get an allowance of 2 thousandths. So what the 2 thousandths is and the term allowance means, that means in the worst case tolerance analysis, which means what we're having here is we're taking the smallest hole and we're subtracting from it the largest shaft. Smallest hole minus largest shaft is the allowance, which is essentially the minimum clearance. Okay, and that would be the tightest fit. So the allowance is the minimum clearance, and that gives you the tightest fit. And this is another example of fits between mating parts. Okay, so a clearance fit occurs when an internal part fits into an external part with space or clearance. Okay, so what I'm saying is when in all cases the hole is bigger than the shaft. Okay, that is a clearance fit. In all cases the hole is bigger than the shaft. Now if we compare that to an interference fit, this means in all cases the hole is actually smaller than the shaft. Okay, so the parts have to be forced together. So this is called an interference fit. Okay, so if we take the hole and we subtract from it the shaft and we get a negative number, that is an interference fit. In a clearance fit, we're going to take the hole and we're going to subtract the shaft size, and it's always going to be positive, and that means that it's always a clearance between those two parts. And we're going to talk more about that and fits between parts and as part of your homework assignment as well. So let's talk about limit dimensions. Okay, so limit dimensions are a method of directly specifying the tolerance by providing the dimensions of the upper and lower limits. Okay, we talked about a nominal size and then applying a tolerance to it. And when you're using a limit dimension, you're specifying the dimension in terms of its limits. Okay, and that's just specifying the min and the max. Selective assemblies. So this was a means of putting parts together, and really what they were looking for is, hey, you put all the parts together and you find which ones that fit better. Yeah, we don't like to do that because it drives up costs. So what we do is we design the fits such that all of the parts, when we pull them out, even though they're made with their tolerances, have the fit that we need. Okay, so we don't do selective assembly. I'm going to end this movie here because I want to start talking about the shaft versus hole system, and I'll pick that up in the next presentation.